Hey, fancy seeing you here. Woo. Okay, this one will actually be shorter, not a hard goal, but okay. Couple of things that I wanted to look at that didn't really fit into the last stuff, and also wanted to give your brain a break. So this is very frequently how you're actually going to be dealing with a least squares regression line, which is to say you're not going to have the data. You're going to have the regression output of processing of the data. So this is, if you want to make an LSRL from a regression output, that's a regression output. All this nonsense. So the situation here is that you can measure lead concentration in a fish in parts per million and use that to predict zinc concentration. So it tells you the response variable is zinc. That means your explanatory variable is lead. Now, this can look super intimidating, but we actually tend to use not too much of it until much, much later in the course, if at all. Like I would say you can get away with not using most of this most of the time. I'd like you to understand it, but one thing at a time. So, first thing I want you to do, right here where it says coefficient, that's good stuff. This is what we want. This is what we want. We might also be interested in this. Everything else, I don't want you to use those numbers. We're not going to use those numbers until Unit 9. Unit 9 is one of the things the College Board is ditching, by the way. So we're not going to use these very much at all. I also want you to cross out that. I want you to physically cross it out with your annotation tools or on your scratch paper, write down just what you need because every year, no matter how solidly we do this, people still want to use these numbers. Don't. Just these ones, just the coefficients. Okay. So to write our least squares regression line, we're going to use our form y hat equals a plus bx, where y hat is, where a is the y-intercept and b is the slope. Now, the y-intercept does not have a variable with it, right? The slope has a variable with it. What do we call the number that goes just to the left of the variable? It's a coefficient. What do we call a number that's not attached to a variable? That's a constant. Constant. So our slope is going to be the coefficient on the explanatory variable. Whatever this is, in this case, it's lead. It could be inches. It could be years. It could be anything that makes sense as an explanatory variable. That's the number we're using. And then for our constant, for our y-intercept, we're going to use the coefficient that goes with the constant. It almost seems silly to call it a coefficient, but just roll with it. So this is the number we use. Now you'll notice, just like it goes a plus bx, this is a and b. Goes in order. So to do this properly, we would say y hat is equal to 16.3 plus 19.0 x. Since we're using x and y, we should say let x equal the lead concentration in parts per million, and and let Y equal the zinc concentration in parts per million. All right, we want to define our variables. If we wanted to write this without defining variables, what we could do instead is say the zinc predicted value is equal to 16.3 plus 19.0 times the lead ppm. And maybe we should say that this is zinc ppm. All right, same exact equation. We still have a slope of 19. We still have a y-intercept of 16.3. But now we're using our words instead of our variables. Okay. Least squares regression line from regression output. Slope, y-intercept. The other thing I boxed here is this r squared. So notice that we don't have r. Can we find r if we have r squared? I hope you're all saying, yes, of course we can, and really freaking out the sub. So yes, we can find r if we have r squared by taking the square root. That's right. So if r squared is equal to, now this is a percent. We're going to write that as a decimal. R squared is 0.82. When we take the square root, r is going to equal, probably take the square root here, 0.82. R is going to equal 0.91. Now, one thing I have to check, because a squared value is always positive. Looking at my slope, right? My slope is positive, so my R I'm going to leave as positive. If in my regression output I notice that the slope is negative, when I take the square root of R squared, I'm going to get a positive number, but I'm going to use my intense intellectual power to know that, the slope was negative and R, or our correlation coefficient, has the same sign as our slope. A negative correlation coefficient goes with a negative slope. So I would change this to a negative sign if I saw that my slope was negative. Okay, so that's R from R squared. Now, how do we get to this handy dandy output? So glad you asked. Cool. So, situation is real, weights are not. All good in the hood. So a couple years ago, I was running a field ecology program and we went on a backpacking trip in North Cascades. We got to go along the Pacific Crest Trail, spend a few nights by the river. It was glorious. Go over some like really sketchy bridges. So we're looking to see if there's a relationship between body weight and backpack weight. There should be. Ideally, you shouldn't be carrying more than, a fraction of your body weight as your backpack weight, just to preserve your knees. It doesn't seem to matter now, but it will. So let's say we wanted to calculate the LSRL. Putting this into a handwritten equation is tedious and a waste of your time. It's possible, but don't do it. What we're going to do instead is use our calculator. So I'm going to have this. And just like before, we're going to enter our data in our list. So we're going to click on Stat. Notice, not second, just Stat. You just click that button. We want to get to this menu. So then we're going to click on Edit. And we're going to put our X values in list 1 and our Y values, the corresponding Y values in list 2. It does not matter what order you put them in. So the numbers could go from lowest to highest, highest to lowest, be all scrambled. It does matter that, for instance, a given body weight of 120 had a backpack weight of 26. Those two values need to be on the same line. So what that looks like, and I think this is question 25, so this is getting you started on your classwork. So our X value of 120, Oh, I have to use the buttons, okay? Goes with a y value of 26, and so on and so forth. So I'm going to type my x values in. So I have 187. No, 187. There we go. 109, 103, 131, 165, 158, 116. Okay, so there were 8 students in that group. All right, then their backpack weights. 26 for the first one, 30 pounds for the second one, 26, again, 24, 29, 35, 31. Oh, that's going to mess up my data. 31 and 28. Okay, so I've entered my data. Now I want to calculate my LSRL. So I'll go to stat and I'll arrow over to calc. We're not doing 2var stats. I don't think we're ever going to do 2var stats. Leave those alone. What we are doing is linear regression now. There's 2 options for this. You have ax plus b and you have a plus bx. Technically speaking, these will give you the same things. They're both correct, but the way you're going to see it on my tests and from the College Board is this version of a plus bx. So y-intercept plus slope times x. So we're going to select option 8. And you could also just press the button 8. Now, it's probably set up for you. X values in list 1, Y values in list 2. It makes more sense that the body weight is going to predict the backpack weight than, or is going to explain the backpack weight than vice versa. This is one of those, like, yeah, it could sort of go either way, but like, you have a certain backpack weight because of your body weight. You don't have a certain body weight because of your backpack weight. So that's the relationship we're looking at. So I put my body weights in list 1. I put my backpack weights in list 2. Those are my X's and Y's. I don't have a frequency list here. I could store the regression equation. Now, frankly, this might be something you choose to do in Desmos instead. I think regression is something that Desmos does really well, but I want you to know how to do it on your calculator as well. If you're going to be mapping with lines and such, use Desmos. Then we're going to hit calculate. And there we go. Now, we have some stuff here. So for our y equals a plus bx, and this doesn't have the y hat. The calculator just doesn't, but you always want to write it. We know that a is equal to 16.26 and b is equal to 0.09. But I don't see r or r squared. So I am going to click on mode. And then down here where it says stat diagnostics, those are off right now. I want to turn them on. You want your stat wizards on and you want your stat diagnostics on. And I'm going to exit the mode. So I just did second quit. And I'm going to go back to stat and calc. So I do need to recalculate, but I don't need to enter my data again. It's already in the lists. So I just went to stat, over to calc, down to linear regression a plus bx. And now I can see my r squared and my r. So my r squared is equal to 0.63 and my r is equal to 0.79. And so I wrote those down. In this context, my regression equation then is y hat is equal to 16.26 plus 0.09x. And that is for x is equaling body weight and y is equaling pack weight. And if I wanted to do my interpretations here, So for the slope, I'm going to type these because I think my handwriting is starting to die. I'm going to move that here. Delete that. Oh dear. Where'd you go? Okay. So our slope, we could interpret it as, we could try to, for each additional pound of body weight, backpack weight is predicted to increase by about 0.09 pounds on average, right? Very, very qualified. I said it's predicted. I said it's on average. I said it's about. All of those things are letting me know, letting an AP reader know that this is a predicted value. It's not set in stone. The y-intercept here for a body weight of 0 pounds, not a living soul has a body weight of 0 pounds, and certainly not one carrying a backpack. So we'll get to that in a second. So for a body weight of 0 pounds, the predicted backpack weight is 16.26 pounds. This is nonsensical in context. So this y-intercept does not make sense in context. So if you're asked, does the y-intercept make sense in context? This is a really great example of something that doesn't. Okay. Then for r squared interpretation, last thing. So r squared. So that's our 0.63. So we'll say that 63% of the variation in backpack weight, I'm going to say variability in backpack weight, can be attributed to the variation in body weight, right? So some of the differences in these backpack weights is due to the different body weights, about 2/3. There are other factors that influence backpack weight. Maybe this person with the 24-pound pack has a super light sleeping bag. They're also pretty small, but maybe that's super light sleeping pad or sleeping bag. Maybe this person with the 35-pound pack, yeah, their body weight's a little heavier, but they're lighter than this person, but they're carrying a 35-pound pack. Maybe they're super strong or wanted to carry all of the kitchen gear or whatever it is, right? There's some other reason that this is higher than that, even though we wouldn't necessarily expect that. So a lot of the backpack weight is explained by the body weight, but not all. So that's what we're talking about here. Okay. You have been gentle people and scholars. I hope you're having a wonderful Thursday, Friday. I hope you have a wonderful weekend. I hope you never see this video because I'm there at school. All right. Good night. Good luck. Where's my recording?